according to our nomenclature rules, we have a covalent bond between the hydrogen and the fluorine because both hydrogen and fluorine are nonmetals. Right? Because they're nonmetals, we've got a covalent bond and we can name it according to those rules. Okay? If we now want to understand something about the reactivity of this molecule, how does it act in solution? How does it interact with other molecules? To figure that out, we have to know something about where the electrons exist on hydrogen and fluorine. And in particular, what we want to know something about is the bonding electrons between hydrogen and fluorine. To understand where those electrons put their highest priority, what we're going to have to do is look at electronegativity. So if we look at the fluorine, I got a seat right up here. I know it's really close. If we look at fluorine, it has the highest electronegativity, okay, which means it wants bonding electrons. So what's it going to do to the electrons in that bond? It's going to hold on to them and effectively draw them closer to the fluorine. One of those electrons came from the hydrogen. If the fluorine takes that electron, what happens to it? The hydrogen becomes more positive because it's now lost an electron, but our fluorine has now gained an electron. And so we can end up generating these charges. Because they aren't formal charges, we have to put that little delta symbol in there. So there's our determination of our partial charges. Now when we try and predict something about how this molecule reacts, we can look at it and say hydrogen being positive wants to react with something that is negative. Right? Fluorine being negative should react with something that is positive. Okay? That simple concept of just positive finds negative, okay, carries through almost all of chemistry, okay? And in particular organic chemistry. A massively important concept. Okay? So it's really, really important to be able to evaluate these partial charges. The next part about it, or interesting aspect of this, is that we then need to be able to draw the structure so we can see where our electrons exist. So that's where we've got all these rules for Lewis structures. Fight me as much as you want on what rules you want to use. I don't personally care. But if your answer is wrong, I will go back to the rules and say you did not do this step. That is why your answer is wrong. Okay? The rules I've outlined are there for a reason because they get you through to each of the individual structures that you may need to determine for an individual problem. Okay? So practice, you'll pick up the rules and you can go through and apply them. Okay, so what we'll do is look at a couple examples. And in fact, I'm going to pause the lecture already, and I'm going to give you guys another opportunity here to work together, talk amongst the people around you, and try and determine the Lewis structures for these three compounds. Right? And as a giant red flag, you want to be very, very careful with that first structure, particularly if you've seen it before and you've done that Lewis structure before, particularly if you got help doing that Lewis structure before, because your help was wrong. Okay? So, Spence is why this one's tricky. If you talk to anybody in the tutoring center, because they've gone through a whole bunch of chemistry, they don't realize that you haven't, which means they give you an answer that you have no ability to replicate. Okay? So this is why the rules are here. Follow the rules, and you get the correct answer. If you go through and use the tutoring center, they had better explain to you why they got a different answer. If they can't explain it in a way that makes sense to you, don't accept it. Okay? So, within these rules, we start by totaling the valence electrons. So I went through and did all of that, added those all up. Okay? In theory, I did the math right. Okay? Once we've got our electrons, we'll pick our central atom, drawn all those out, and we scattered the other atoms around it. And then we'll start adding our electrons into the structure. That's my fault. Starting with the most electronegative atom. So for our sulfate ion, we can start putting our electrons in around our oxygens. Okay, and we can continue to add. And how many electrons do we put in around each oxygen? Why 8? Because of our octet rule, okay, which we will be breaking in just a little while. This is why I didn't include this on the first exam. All right, so there's our 8 electrons around each oxygen. How many electrons have we drawn in? We got 32, so we're now done with adding electrons, so we'll convert any pair of electrons between atoms into a line to represent a bond. Okay. For lab reference, what we've got drawn up there right now is the Lewis dot structure. If we wanted to convert that into the molecular structure, we now convert those into our lines. Do our oxygens have octets? Does our sulfur have an octet? What do we do now? We should officially put in our formal charge, which you'll sometimes see with the full brackets all the way around. You'll notice that I am exceedingly lazy, and what I'll typically do is this. There's my little corner for a bracket, followed by my -2. Okay, giving you the same information. Ask a tutor to go through and provide the Lewis structure for this. Guaranteed what they are going to give you, well, hopefully guaranteed, will be this structure. Which of the Lewis structures is correct? It's a hard question. Both of them are correct. Which one is correct for this class? The first one. Okay? Because you have no reason to go through and make double bonds. Okay? The only reason we make double bonds is to satisfy octets. We've got our octet satisfied. We're done. Okay? This is our final answer. So why did they go through and draw the double bond? Because Rule 7 is to assign formal charge per atom. You're not required to do that, which means you don't have the tools to realize that this structure, as we've got it drawn, is actually better than the previous one. When we go through and draw Lewis structures, we assign a formal charge per atom. Then our very last step is do whatever we got to do to minimize that charge. Okay? So, yes, go ahead and ask your question. There is, as far as what you guys need, there is no other structure.
Well, there is if you do it the other way.
That's the wrong answer. So if you provide me the double bonds, you don't have those tools to explain why you need the double bond. If you don't have those tools, when you provide that answer, what did you do? You necessarily cheated. Okay? There is no other option, okay? Because you don't have the tools to be able to get to that answer, which means you had to have cheated.
Well, I mean, horizontal and vertical. Don't put both of them like that.
I don't understand. What's horizontal or vertical?
Well, you know how you put the double bonds on
The double bonds is a wrong answer as far as you're concerned.
Well, I mean,
Okay, so you cannot be drawing the double bonds. You have no tools to say why this answer is incorrect. So this answer is your correct answer. There is no resonance. Everything has satisfied the octets. Follow the rules provided. Okay? I know everybody's going to hate that, but this is why we gave you the rules. Okay? We're trying to simplify Lewis structures so you don't have to know new rules, hence the big strike through in your table. Okay? So you don't have the abilities to go through and do that, so don't do it. Don't go through that extra work unless you're told to go through and do it. When will you be told to go through and do it? 151 or organic chemistry. You're not in that class. Okay? If you want to move to that class and do the more difficult things right now, you can try and switch in now. You're in 130. Keep it simple. Okay, there was another hand. Yeah.
Sulfur has 6 valence electrons. So why does this work?
When we draw Lewis structures, when do we determine valence electrons? At the very beginning. That's our first step. When do we look at valence electrons again? We don't. Okay? So I don't care that sulfur has 6 valence electrons to start. This isn't sulfur atom. This is sulfur bound to 4 oxygens. Its valence electrons are irrelevant. Okay? The only reason we add 6 in is at the very beginning to figure out how many valence electrons we've got. Okay? Simplify the rules. Okay, more questions on that? Okay, as a real quick kind of prelude, you are not responsible for this, but if you go through and assign formal charges on the atoms in this structure, you end up with oxygens all being negatively charged, and the sulfur being a +2. What do you think? If our whole goal is to minimize charge, is that a good structure? No. Every single atom has charge. So what do we end up doing? We move electrons from the oxygens into bonds with the sulfur. The net result is oxygen loses 1 electron, sulfur gains 1. Another oxygen loses 1 electron, sulfur gains 1. The net result is that we lose our charges on 2 oxygens, and we gain 2 double bonds. If we were concerned about resonance now, yeah, you've got a crap ton of resonance within this ion. Okay? Some ridiculous amount of structures. Okay? I'm going to guess 6. Okay? You're not responsible for knowing that. What you're responsible for doing is getting all the way up to charge, and your responsibility is to put the charge there. Okay? You do not have the ability to take it to this structure. Okay? I'm trying to make it easier. I know you don't believe me, but I'm trying. Yeah.
Okay, so with that structure, you don't have to put the brackets or anything. So you're
this structure is, oh yeah. Because we've put the charges on the individual atoms, we don't need to put the bracket because we've already specified where those charges are. Exactly right. Okay? So when you draw out your Lewis structures, you do not need to assign charge to an atom. The correct answer, once again, all the way back through to this. Oh, it actually didn't move the lone pairs in. -2. There you go. That is your final answer. Yes?
Okay, so I'm not fighting you on this, like I understand that this is the answer. But Edward, okay, so like I was taught the other way, but like if I did put the charge per like atom, technically would that be right? Because isn't that like the tools that you said?
Yes. So if you have the ability to reuse those tools, you can absolutely go through and do it. So on an exam like this, if I had asked for what's the Lewis structure of sulfate, I would have immediately circled it, and when I handed it back to you, I would say, here's a new problem. Give me the Lewis structure. If you go through and with that new problem, go through and assign all the charges and double bonds correctly, I'll give you credit.
Okay.
If you don't, then you had it memorized, and you memorized it from a wrong way to apply it.
Okay, because like on the test I did it, I put like I did the
Test was a different situation. So when we talk about dealing with double bonds, on the test you had to do this because the carbon did not satisfy its octet. Okay? So this is a case where all atoms satisfied their octet. We don't do anything else. On the test you had carbonate or sulfate or SO3, something like that. I don't remember which one everybody had. It was carbonate. Okay? With carbonate, carbon was missing its octet. You had to shift electrons in. That's 6. Does that make sense? And we will draw that Lewis structure up in a little bit too. Okay, more questions with the sulfate. I know that irritates everybody. I sort of apologize for that. Kind of a backhanded apology, I guess. Okay? So let's move to the next one. PCl5. Anybody immediately have an issue with this? Hopefully, yes. Okay. When we talked about Lewis structures, we looked at our central atom being a square. 4 possible locations to put a bond. Why? Because when Lewis first tried to determine structures, he simplified and looked at the first 2 rows. Within the first 2 rows, we can only get 8 electrons into that second energy level. What happens when we move up in energy level to row 3? How many electrons fit into the 3rd energy level? It's a trickier question. 18. 2 from the S, 6 from the P, and 10 from the D orbitals. Because we've now increased the capacity for electrons, guess what happens? We increase the capacity for putting more atoms in there around as a bond. Okay? So when we exceed that second energy level, or our central atom is in an energy level higher energy level but lower on our periodic table, okay, then we can exceed the octet, okay, which is why sulfur could have those two double bonds. Okay? So when we move through to our phosphorus chloride, we now pick our central atom as our phosphorus, and we drop the chlorines all the way around it, and we go through the same process that we've done before, and we put in all of our electrons. Do I have to draw this one out? Fair enough. Anyone want to sing while I'm waiting to draw all these in? Take that as a no. How many electrons have we got drawn in now? We've got all 40 electrons in, so we can't add any more electrons. Now we will go through and draw bonds where we have pairs of electrons between our atoms. Okay? And we've got our final Lewis structure. You'll notice that we don't have just 4 bonds. We have to have 5 bonds. Why is phosphorus allowed to have 5 bonds? It's in that third row. Because it's in that third row, it can expand its octet. That expansion allows it to have 10 electrons around it. Okay? Everybody glad I didn't put that on the test? Yeah, see, I'm not a horrible person. All the time. Okay? Questions about that structure? Okay. We are then done with that one. There's no point in dealing with octets anymore. Our phosphorus has exceeded its octet. The chlorides are all at their octet. We're done with that structure. Okay? We move to the next one. This one doesn't look too bad, right? We just got 4 bonds. That makes sense. How many electrons do we need to put in? Did I actually do that math right? Yeah? Okay, good. I didn't actually know. So we can go through and now start putting our electrons in. Where do we start putting our electrons? Fluorine. And as I'm doing that, kind of delayed. Anybody have any direct issues with this when you first saw that formula? When you first saw the formula, not the looking at the electrons. But yes, we will have 4 left over. Xenon's a noble gas. What do noble gases do? Don't react. That's a bit odd. Why is xenon making a bond? Where is it on the periodic table? Column 8 and at the very, very bottom of the periodic table. It now gets so large that while it may be a noble gas, it's big enough that it can form some bonds. Okay, crazy. How many electrons have I put into the structure? 32. I'm 4 short. Where do I put those last 4 electrons? Okay. Before we can put them in bonds, let me go through and draw in our bonds. So you want to put them, say, in that bond and that bond, maybe? Is that the suggestion? Okay. How many electrons are around the fluorine? That far right fluorine, how many electrons does it have? 10. Where is fluorine on the periodic table? Ours. On the right side, second energy level. How many electrons does it need to have? 8. Can it exceed its octet? No. You cannot put the electrons into double bonds. Did I just hear stupid? Okay. So where do we put them then? If the fluorines can't take them and our bonds can't take them,
Can you add another?
we can't add another element.
Can you put them to another?
Put them on the xenon. Where is xenon on the periodic table? The very bottom of it. Is it in energy level 3 or greater? Yeah. Can it expand its octet? Yup. So we can put those lone pairs then on the xenon. So now the question is, how do I put them in there? Do I go through as just one? Whoops, that's an eraser. 1 electron on each side? That's prettiest. Fair enough. When we go through and put in our electrons, we put them in pairs. Okay. There's our the Lewis structure for our xenon tetrafluoride. Okay. Much more advanced. I want you guys to at least see it. I don't think it's going to show up on the final. I don't think I'll ask questions on these harder structures on exam 3. You can fully expect to see Lewis structures show up on exam 3. Okay? But I will stick with these simpler versions of it that we've already been tested on. Okay? The idea is to show you this so that you are now aware of what's happening within these kind of more bizarre structures. If you move into 151, you get to do this all the time. If you move into organic, you don't have to worry about it because we deal with row 2. Okay? Questions about what's up there? Yes?
With the extra pairs of electrons on the right, lower left.
So as far as where you put those electrons, our Lewis structure does not imply shape. So it doesn't really matter where we put those electrons. Okay? As long as we put them in as pairs, you'll notice that I put them on opposite sides because we want the electrons as far away from each other as possible, but it doesn't really matter as long as they are distinctly 2 pairs of electrons.
So I guess my question was, when we were reviewing, you said that like there were 3 possible answers and they had to all be there.
For resonance. This isn't resonance. Resonance deals with double bonds or triple bonds. Okay? Deep breath. Not that bad. Okay, it is kind of bad. Okay? What's the next thing that follows Lewis structures? Starting to confuse them all together there. Shapes. You got the right idea. Molecular shape and electron geometry or electron shape. We bring in the geometry because shape is too simple of a word, so we have to call it geometry just to make it more difficult. Okay? So with each of our structures, once we've got a Lewis structure, we can then start to evaluate something about the shape. Okay? And that's where we ran into all of these individual images and shapes that came off of it. Okay? So let's go through and deal with some examples. CO2 is a new one. So I'll give you a couple minutes here to go ahead and draw out the Lewis structure for CO2. And then we'll go through and look at the shapes for all 3 of those molecules. Okay? In theory, what you came up with for the Lewis structure, nearly everybody picked this up to here. Right? What's the issue with this structure?
Carbon.
Carbon doesn't have its octet, so what do? We'll move a pair of electrons into forming a double bond. Okay, so we now have the Lewis structure for CO2. So, dealing with shapes. Okay, with shapes, what we look at is our electron geometries first. Okay, so let's start simple, because you're going to be responsible for everything above this red line. Okay? And if we look at above that red line, how many groups of electrons are around our tetrahedral shape? 4. How about the trigonal planar? Linear? 2. Okay? So those fall under Lewis's envisioning of our structure. And Lewis envisioned it as a square, right? Each of the faces of that square is now a region. Okay, so look at each of those regions. How many regions of electrons are around the carbon? Okay, so I'm going to get a lot of people giving me 4. So let's go ahead and start with a region that has electrons. Does this region have electrons? Does this region? Does this region? No, there's nothing there. We can't have a region of electron density if there's nothing there. How about the one above? So how many regions of electrons are there? 2. And only 2. With that information, we can now go back up to our structures. We said our tetrahedral had how many regions of electrons? 4, trigonal planar. 3, and our linear? 2. CO2 had how many regions of electron density? 2, which means what shape? Linear. You're done. Okay? So when we look at the electron geometry, there's only 2 regions. We've got a linear shape. Okay, so I'll abbreviate that as EG for electron geometry, and we have linear. As Nick was alluding to, we also have molecular geometry, which we'll call MG. Okay? In molecular geometry, we're now going to distinguish between non-bonding pairs of electrons and bonding pairs of electrons. So when we go back and now look at our regions, region number, let's go ahead and number them. 1, 2, 3, and 4. Region 1, is that bonding or non-bonding? Bonding. Region 2, bonding or non-bonding? Bonding. Do we care about 3 and 4? No, because there's no electrons. So what shape necessarily correlates to that? Still linear. So our electron geometry and our molecular geometry are exactly the same. They are both linear. Okay? Before we get into the more complex ones, let's pick another example here. If we went through and did NH3, so I've been doing this one a lot. Whoops, don't do that. NH3. We draw out our Lewis structure. What do we get for our Lewis structure? Eraser. Nitrogen, hydrogen, 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 non-bonding pair. Draw in our box around our nitrogen. How many regions of electron density are around the nitrogen? 4, which means the shape is tetrahedral. Okay, so our electron geometry, EG, is our tetrahedral. When we shift to our molecular geometry, we now distinguish between bonding and non-bonding pairs of electrons. So we go back through and look at this. How many bonding pairs of electrons are there? 3. How many non-bonding pairs? 1. What we would then do is go through and look at our other options. The geometry that matches that is our trigonal pyramidal. How do you know it's trigonal pyramidal? Okay, we have 1 non-bonding pair, which ultimately means you're just reading the table, okay? Which is good. I want you to do that. Okay? How would we know that without the table? You really wouldn't. Okay? All of these names for the shapes have come from somebody actually building a 3-dimensional model and looking at it and saying, that looks like a pyramid. But that pyramid only has 3 atoms as a base, so I'm going to call it a trigonal pyramid. And you are now responsible for that information. Okay? Yeah, yippee. So when we move into lab, you will be doing a lab that involves these. We've got model kits in the lab. I'm going to bust out the model kits. For anybody that is not in my lab, ask your instructor to bust out the model kits as well. Okay? If you want to use them. It will help you see what's going on with these shapes. Okay? There was a question.
So only for the molecular geometry, we still need to know the electron geometry because we need to, the difference between pyramidal and planar.
Yes.
We know that there's something in that fourth region, it's just not
Yes.
showing up in your one.
Exactly right. So to determine the molecular geometry, you still need to know the electron geometry. Because the electron geometry is what helps you sort into the proper category. Okay? Questions with that one, or should we pull another example out? Let's pick PCl5. Do I need to draw a PCl5? You just like watching me draw dots, don't you? So there's our PCl5, which you should already have in your notes, so thanks for making me draw it again. I need to practice, right? So we now go through and look at our PCl5. This is one where we run into an issue. Remember, Lewis is all about squares. Can we do that with this object? No, because we can't have 5 sides on our square. And we're not going to even move into a pentagon or anything like this. What we'll do now is just say how many regions of electron density are around that phosphorus. 5. We have 5 distinct bonds, 5 regions of electron density. What shape matches our electron geometry? 5 regions of electron density puts us into the trigonal bipyramidal, or pyramidal, it doesn't really matter. Okay? So we now have that overall shape. What's our molecular geometry? I can't even spell bipyramidal, whatever. Bi-P, there we go. Okay? We now look at our groups of electrons. Do we have a difference? Are they all bonding? They're all bonding, so there's no need to look at non-bonding effects. Our molecular geometry ends up being the exact same as our molecular geometry. Both of them are trigonal bipyramidal. Okay? So it's a question of evaluating your center atom and saying what things are around it, be they bonding electrons or non-bonding electrons. And then pulling from some table what shape best matches that. Okay? Xenon tetrafluoride, we did that one as a last example, just because that's another kind of weird one. Sure, why not? I like the enthusiasm. It really gets me going in the morning. Wakes me up. How many regions of electron density around the xenon?
6.
There are 6 regions of electron density because we have those non-bonding pairs. So 6 regions of electron density. Our electron geometry is octahedral. We now look at those regions of electrons and say, okay, is there a difference between them? Do we have bonding and non-bonding? Yes, we do. We now go through and match that to square planar. And our molecular geometry is square planar. Which is interesting, because we have 4 bonds, right? Well, methane had 4 bonds, CH4, but that was tetrahedral. Why does the shape change? The non-bonding pairs of electrons occupy space which force the other atoms into different arrangements. Right? That's why we have to look at the electron geometry, not just at the bonds. Okay? Yippee! Okay. What I fully expect you to be able to do is to deal with your linear, trigonal, planar, and tetrahedral shapes. Right, so I've got those listed out for you in kind of a table format that I think is a little bit easier to read than that figure that I had up there just now. But that figure also shows what it looks like. Here we don't get to see what they look like, but we can at least sort through it a little bit quicker to what those individual shapes are called. Okay? So you are responsible for all of those shapes. Yippee again. Questions? Are you all now like really angry at me? Okay. Takes practice. For those of you taking pictures, I appreciate that my slides are so beautiful that you want to take pictures of them, but they are posted online, so you don't have to take pictures of them. Okay. You can, it's fine. I'm just saying. I can stand next to it, we can get some added value. And now you put the camera away. Okay, well, now I understand. Okay. The rest of, what are we in? Chapter 12 talks about a couple extra concepts. Coordinate covalent bonds. If we go through and look at Lewis structures, a coordinate covalent bond technically is showing up in the case of ozone, but those are most classically looked at in different structures. All that's happening is that we're saying one compound or molecule or atom is supplying the electrons to a bond, okay, in both electrons. It's a really minor concept. Don't stress too much on it. All we're looking at is that O2 in this case is providing the pair of electrons that allows for the bond to make ozone, O3. Okay, that's really it. Okay? It becomes a lot more important if you moved into real inorganic chemistry, because in real inorganic chemistry, we're concerned about where d electrons are and the transition elements, and those transition elements do a lot of coordinate covalent bonds. Okay? And that explains a lot of the colors that we see. A lot of the colors in individual solutions comes from the transition elements and how those electrons jump around. Okay? More importantly, okay, and this drives me up the wall because the book makes it look like a bond, so we're going to take a step back from that first. There's a concept of bonds and there's a concept of forces. These two things are different. Okay? So if we look at an interaction between atoms, we could go through and look at the bonds, and we could say we have an ionic bond versus a covalent bond. Okay? But what if we don't formally form a bond? Okay? Is there still some attractive force or repulsive force? Yeah. So what we end up going through and doing is labeling those forces as well, or those interactions. So the example starting off here is with carbons and hydrogens. I thought that was a little boring, so we could turn it into little emoticons. We've got two random atoms, or we can even look at it as people. Okay? Far enough away from each other, no interaction happens. But what happens as they get a little bit closer? Oh, maybe they start to get attracted to each other. That now weak attractive force starts to bring them closer to each other until eventually, maybe they start dating, and then maybe they get married. Okay? So what's happening is we're looking at individual attractions between those. And in each of those cases, we can come through and evaluate the level of attraction. Most typically, we would hope that married people have the strongest attractive force. Right? That's why they're married. Okay? Couples are probably a little bit less attracted to each other because they haven't made that full-on commitment. Okay? When they're just ogling each other, or I don't know what those are doing. Okay? Okay? We do still have some attractive force, but they aren't really a couple. They haven't actually formed any kind of real strong interaction yet. And then we've got them entirely separated away from each other where there is no interaction. We've gone through and called each of those stages different things. Wedding, married, couple, dating. Okay? Who gives a crap who you are? Okay? We've established those individual rankings within it. Atoms have a very similar process. And so when we look at how atoms interact, just like we look at how humans interact, we go through and label the varying stages of that. When we look at bonds, we had the ionic, the polar covalent, and the nonpolar covalent. All of those are the strongest attractive force. So those are subcategories of our married group. Okay? That coupling one is a little bit of a weird one. Okay? Because we actually have formed a couple, but they aren't completely committed. So we end up throwing in a new kind of weird interaction in there. Okay, that weird interaction, very thankfully, gets a new name. And by new name, it's exactly the same. It's referred to as an ionic bond. But wait, didn't I just say married was a bond? Yeah, I did. So what is ionic bond up here if it's not here? This ionic bond is not technically a bond. Yeah, I know. It's the attractive force between two atoms that have not formally started sharing electrons. So ionic bonds float in this weird gray area between actually being called a bond and not being called a bond. Okay, so I'm personally not a fan of ionic bonds for that reason. Okay? If we wanted to change that around a little bit, we can get that same information by calling it electrostatic. Okay, so you may see that float out there as well. It's the same idea. What we're looking at is ionic, not bond. What we're looking at here is a force. Okay, well, bonds are forces as well. They are a very strong, attractive force. Okay, it's just a weaker force. What happens when we move even further up? Now what we full on do is move into actual forces, okay, that are, again, not bonds. We subcategorize our forces into a sequence of other possibilities, okay, which we will, I think, talk about later in the semester. We've got our hydrogen bonding. Yeah, I know you love that term. Hydrogen bonding, dipole-dipole, and London dispersion forces. Since we will talk about it later, I'm not going to write it out, LDF. Right? If we have no interaction whatsoever, that's when we're up at the top, no interactions. So it does kind of parallel human interactions, or how we've classified human interactions. Okay? The relationship between all of those is ultimately just looking at how close individual people got to each other. Same thing happens for atoms. How close are those individual atoms? Okay? We can use that information to start to predict something about the chemistry, and what we see is a complete spectrum of interactions. Okay? So when we do get into this, that's what I'm showing here. We're looking at a distinct difference between bonds on the left and forces on the right. Okay? On the left, we actually have a married couple. And on the right, we just have dating. Okay? If we know something about the bond, we can then determine something about the forces that that molecule can exert in other cases. Okay? One of the most important forces, which is why your textbook devotes a section to it, is this one referred to as hydrogen bonding. Okay? Any ideas why I might object to the name of hydrogen bonding? It's not a bond. It is a force. Okay? Be very, very careful with that. So when we look at the Lewis structure chapter, it's all about bonds, and for some reason they throw in hydrogen not bonding in as a bond. It's not a bond. It's a very, very strong attractive force, okay, that involves hydrogen. Okay, we started today's lecture off by looking at electronegativity and the partial charges that are generated from that. Any ideas what structures are shown in that right-hand corner? What was that? Water. Okay, we've got hydrogen in white, so I'll go ahead and write in white hydrogen. Come on. Hydrogen is our white color. Not even after I said come on, you didn't even leave me alone. Oxygen is our red color. So we've got H2O in both cases. Okay? What charge does our red oxygen build? I heard a negative. Why does it build a partial negative? It has a much higher electronegativity than the hydrogen. So the oxygen becomes partially negative, and our hydrogen becomes partially positive. Remember at the very beginning of the lecture, I said we can use these positives and negatives to predict something about how these molecules interact. Well, now let's take a look at our first water molecule, which we got labeled. Let's look at our second water molecule and label it. What charge does our hydrogen become?
Positive.
Why does it become positive? Because the oxygen right next to it is more electronegative. Very good, which means it becomes partially negative. What do our negatives want to do? Connect to a positive. So when we look at two water molecules, we expect them to align where the oxygen aligns with the hydrogen, because that connects the negative to our positive. How strong of an attractive force would that be? Should that be a really weak force or a really strong force? So as an opposite idea, I know this is a long distance one, let's look at the attractive force between my now colored in blue hydrogens, which both have a partial positive charge. What strength of attractive force do we have there? Is there an attraction? No. If anything, there's a repulsion. So if we look at the interaction between our hydrogens, we would say no interaction. We look at the interaction between our oxygen and our hydrogen, we say relatively, that is a much stronger interaction. Hydrogen bonding is such a strong interaction that it gets included in this bonding chapter. It is not a bond, it is a very strong attractive force. That attractive force is so critically important that that's why we think life must have water. Without water, we don't have life, okay? Because of that hydrogen bonding interaction. It explains a ton of physical properties within the molecule of water, and it allows us to actually exist. Okay, so it's a pretty phenomenally important molecule. We will spend some more time talking about it later in the semester again, but at this point, because it showed up in the book, I wanted to address it so you're aware of what's going on with it. So what types of bonds do we have? Ionic, covalent, and polar covalent, or non-polar covalent. Okay? Where is hydrogen bonding as far as a bond? It's not a bond. Do not call it a bond. I like my hair where it is. I don't want to be ripping it out. Okay? 5 minutes. I'll finish the rest of these slides. Don't panic. I'm not going to do that. Chapter 7. Chapter 7 brings us back to this concept of chemical and physical changes. Okay, so for this next exam, I will warn you, we've got a lot of new material in it, and it's a lot of application of material. So it's going to require practice. It's not just, oh, who did this? Okay, there's no application of who did this. You just have to know it. Here, you have to understand what we're talking about and apply it. Okay, so when we're looking at Chapter 7, they come back to this concept of chemical and physical changes, but now we're going to give you the tools to actually decide a little bit more appropriately whether we had a chemical or a physical change. And we will do that by looking at reactions. Okay? So, big characteristics for chemical changes. Okay, we're looking at a change in phase. This typically means no heat is included on our part. So if we see bubbles form, hey, that's change in phase because that's a gas bubbling out of our solution. Okay? Since we didn't add the heat to cause the phase change, that's a chemical change. Okay? The other one that we could see is a solid being formed. If we mix two clear solutions and it becomes cloudy, that is a solid. That cloudiness prevents light from passing through the solution. Well, what prevents light from passing through? Solids. There we go. Solid. So if we see a solid form and we haven't removed energy from the system, we're looking at a chemical change. Okay? So both those two I classify as the same thing because it's ultimately just a phase change. Your book classifies those as two separate categories. Okay? Other one is a permanent color change. We've got to be a little bit careful with that. This is not a dilution of color. Okay? So if we started with red food coloring and clear water, and we mix them, we do end up with a color change. The solution goes kind of pinky red. Okay? That's not a chemical change. All that was a dilution of the original color. Is that insanely tricky to deal with? Hypothetically, yes. When you're in the lab, no. It becomes rather obvious. Okay? Typically, it's I add a yellow solution and a clear solution, and it becomes red. Well, I don't have an explanation for why yellow should become red, so there had to have been a color change coming from a chemical reaction. Okay? Last one is energy change. Okay? Energy is either released, so we feel the temperature go up, or it was absorbed energy, or we see the temperature go down. Okay? Both of those are signs of a chemical change. Are there other forms of energy? Yeah? Light is a form of energy. If we're looking at a solution that all of a sudden light comes spraying out of it, that's typically a good sign that there was some kind of energy change, okay, which means there's probably a chemical reaction. Okay? When we're looking at the difference between chemical and physical, it is a full-on spectrum. Okay? Just like our forces, just like our rainbow. Okay? It's a continuous spectrum between physical and chemical. Where we try to keep this class is on the extreme sides of it. That's something that is clearly physical or something that is clearly chemical. There are gray areas. We already talked about one. That one being salt water. Okay? So we do have gray areas in between. If, when it comes down to the final, go ahead and cover that up. The final is a standardized test given through the entire chemistry curriculum for Chem 130. Okay? There are at least 2 questions on it that I have strongly objected to. Nobody wants to change them. So do the best you can, and I remove them from the test. Okay, but I didn't tell you that, and there's no permanent record of that because I'm covering up the mic. Okay? Theoretically. Okay? So, if there are things that are objectionable, you just have to let me know. We'll try and work within our systems. Okay, I think I got pictures, yeah. So our picture on the far right, we're seeing, in theory, bubbles there. Not the easiest to see, but we're seeing bubbles come off of that. So there's a chemical change. Here we've added 2 clear solutions, and this yellow weird solid has formed. Okay, that's a solid formation. We also have a color change there. We started with clear solutions, and we've got a yellow solid. Typically, your color changes come with the formation of a solid. So there's usually something else to trigger that you're doing a chemical change. And we can look at energy being released. If we dropped any one of the group 1 metals into water, we'd see a big, massive release of energy. We'd see flames and sparks and all sorts of other fun stuff. Chemical change. Okay? Darn close. States of matter and equations. What information does the following equation provide? Nice open-ended question. What do you see in this equation? Interesting, acid. Why do you say acid? You see AQ, but we said acid actually has 2 things. What does an acid need to have? Hydrogen and AQ. So what did AQ mean? Aqueous. It meant that it dissolved in water. So what we're specifying with that AQ is that whatever substance D is it dissolves in water. We'll elaborate on what that definition means when we get to it. What other information is in that? We know the phases. A is a gas. B is a liquid. C is a solid. What else do we know?
That they together become.
It's showing a reaction. When I add A and B together, something happens. That something happens is my arrow to then produce C and D. So we have reactants and products across this equation. So we've got phase information in reactants and products. So we've got a whole bunch of different symbols. Your textbook goes through and elaborates all of those and tells you roughly where they show up. You are responsible for knowing those. We will be responsible for going through and specifying all the phases. My least favorite thing to do. Okay? And yes, we are done.